All right, so now I want to consider case 2. Case 2, as the book describes it, is where either the torque varies with length or the area of the bar varies with length. And the general equation is that phi is the integral of 0 to L as of the integral of t as a function of x dx over g times I as a function of x. Now in this particular problem, we're saying that the area of the bar stays the same, but the torque varies linearly. It's not a singularly applied torque where the torque is the same throughout. It changes, the total torque changes as we go through the bar. So I'm going to say that in this problem, phi is equal to 0 to L, t of x dx, and then g is a constant, and we're going to say that the moment of inertia is a constant. So imagine in this bar, let's say that each one of these little lines is a singularly applied torque. Let's say that they are individual torques applied. Well, you can see that the reaction over here is going to be the sum of all those little ones, isn't it? Just like we did in the previous problem where we had we had several applied torques. Well, you add them up to get the reaction. Same thing here. If these were discrete, you would add them up together. Since they're not actually discrete, it is more of a uniform distribution, but the maximum of each one is t. So we can say that t times, as x, if you start here, as x gets bigger, the total torque is the sum of those things. So that such that the reaction here is actually t times L. And at any point along the line, you'd say that the total torque here is equal to t. T meaning some number of Newton meters per length, and multiply that by the length, you'd get the total torque of Newton meters or foot-pounds or whatever it is. Okay, so play with that in your head a little bit and make sure you understand that. But the total torque at the end would be, well, the torque at any point along the way is Tx, and then if x is equal to L, meaning going all the way, the total torque is going to be equal to TL, and that's going to be the reaction. If x equals L, T of x evaluated at L is going to be TL, and that's going to be RA. So since the torque as a function of x is equal to Tx, I can plug that into my equation up here, and let's just do that. Phi is equal to 0 to L, Tx dx over Gi. T is a number, it's a constant, it's Newton meters per length. X is my variable, I'm going to integrate x dx from 0 to L. And G is a constant, I is a constant, so I'm going to bring those out of the integral. Integrate x dx, I get 1/2 x squared from 0 to L, and I get this. TL squared over 2GI, and that is my phi. That's the change in length, the total change in length, excuse me, not the change in length, the total the total twist in radians from here to here. And obviously the twist keeps getting bigger and bigger as you go this way, so that out here you got the most twist. In here you have the most torque. If that makes sense to you. The twist keeps getting bigger and bigger as you go. At the fixed end of the bar, you actually don't have any twist at all, but that's where you have the most torque. Since it's fixed there, obviously the bar can't twist because it's fixed. All right. Then, since this was a bar of solid diameter, I is equal to pi over 32 d to the fourth. I plug that into there, and we get this is phi for a solid bar. All right, we can plug some numbers in there if we want, and let's just say that the t as a function of actually that's probably should be Newton meters per meter. Torque is Newton meters per meter. Length is 1 meter. G is, I just put some numbers in here, 50 e to the 9th, and this is in the metric system, and diameter is 25 millimeters. So that would be 0.025 meters. Plugging that into my formula of pi d fourth over 32, I get that, and I can calculate my twist over the whole length of 1.5 degrees. So let me just suggest to you that this is a very common type of condition. Screws into wood. This is the most common that I can think of, where you're screwing a screw in, and the farther it goes, the more torque that it requires. And you know this if you've ever screwed screws into wood. It's a little different than screws into a nut, because the nut doesn't have the same kind of resistance that wood does. But as you go screws into wood, you know, the farther you go, the more torque is required, and you're going to get the highest torque at the top up here. All right. Okay, so anyway, that's the common condition. The next question was, where does the maximum stress occur? Well, the maximum stress is going to occur where the maximum torque is. And we already talked about the maximum torque is going to occur at the very top. So that's where the maximum torque is. And we said that the torque, or the reaction of a bar on a fixed support, the reaction is going to be equal to TL. That's what the maximum torque is. And I can plug that into my tau max equation. Again, R is diameter over 2. Plug that in there and I get 16 TL over pi d cubed. Okay, that's where we have varying torque. I think that's probably as far as we're going to go. I don't think we're going to have any problems where we have a different kind of torque distribution, at least not yet. So now let's look at another piece of case 2 where the torque is constant but the area changes. And when the area changes, the moment of inertia changes. So first we're going to look at a solid bar, solid tapered bar. Clearly it has a different area here than it does here. And so our equation, because torque is now a constant, I can put T dx on the top because torque's constant, but now I varies as a function of x. And because this is a solid bar, we're going to start at either end, doesn't matter. But we say we have a diameter of A and a diameter of B here. Now here's where we did this before, is that the diameter as a function of x, if x starts here, has this little ratio relationship such that dA plus x over L, dB minus dA, is the diameter as a function of x. We've already gone through this in class before, so I don't think we'll have to dwell on this. But if you just carefully look at this ratio, it says that as x gets bigger, it gets closer to L. When x is 0, this term goes away, and we say that at x equals 0, the diameter as a function of x is just equal to dA. It's just that term. As x goes to L, this term becomes 1, and the dA's get eliminated, and dB is the only thing that's left. So at x equals L, the diameter is equal to dB. Pretty easy, I think. But anyway, now that we have this equation for diameter, we can plug that straight into our equation for polar moment of inertia. And we can say that here's my equation for polar moment of inertia of a solid bar, but now the d is a function of x, so I'm going to say that I of x is equal to pi over 32 times this whole quantity to the 4th. All right, so here's where, in order to do some evaluation, you have to get pretty good on your calculator. And let us just make sure you know how to do that. Come to see me on Monday if you don't know how to integrate on your calculator, because you might need to have that skill for the exam. But at any rate, or for an exam or quiz coming up, so it definitely is a skill you need to know. But anyway, so I'm going to say that phi is equal to the integral of 0 to L. And I got my torque, dx, g, pi over 32, then I get this whole big quantity to the 4th power. Now, you could probably integrate that as an integral. That'd be a challenge. I'm not going to require that you be that good at math. I would rather have you be pretty proficient with being able to do this kind of an integral on your calculator. But so I'm going to put just some values in here and see what we get. So I just say torque is equal to 500, g is 4 times e to the 6. That's about what aluminum is. This is in the in the English system. Now I'm going to say the diameter at A, small diameter is 1 inch, the big diameter is 1.5, and I'll say that it's a 24-inch bar. Plug those in from 0 to 24, evaluate this, and you get 0.1418 radians. Now let me just do this integral for you. So I'm just going to do this on my 83, or excuse me, yeah, 83, and let's just make sure I did it right. So I'm going to do math 9, which is the integral, and I'm going to do 1 over this quantity and see what I get. So I'm going to go 1 divided by the quantity, 1 plus, and then I got another quantity, x over 24. So alpha x divided by 24 times the quantity. Well, actually it's 1.5 minus 1, but I'll go 1.5 minus 1. All right, so now I need to make sure I got enough parentheses. I need to close that parenthesis and this parenthesis, and see, that closes that one. This one closes that one. Now I'll do one more, and that will close that one. Now I'm going to raise this whole thing to the 4th power, and I think that should get there. We'll see if it blows up. All right, so now I need to put my functions of integration. I'm going to say I'm going to integrate it in x, and I want to integrate it from 0 to 24. And then I want to close the parenthesis again, and we'll see what happens. Boom. Hey, made it. 11.259, and that's what I had up here, 11.26. Whoa. Sorry about that. My camera just died, went in the wrong direction. I have to retape this. I don't want to do my whole video all over again. Let me put some more tape on here so it doesn't fall off again. Duct tape. Good stuff. Well, it should have been good stuff. It wasn't holding very well there. At any rate, I hope that you can see how to do that integration and hope that you understand that. All right, let's finish this up with a last thing here. And what I just said is the magic in coming up with a formula, or magic in this whole thing is coming up with a formula to integrate. So here is another problem, 3.4-12. Now this one has a tube instead of a solid bar, and you can see that the torques are positive because they're pointing out, coming away. And well, I didn't talk about this before, but in our previous section there is if the wall of the tube is thin compared to the diameter, there is a simplification that we can use. And so in this problem it says that we can use the approximate formula of equation 3-21. So you should look at that. But at any rate, because it's thin compared to the diameter, we can use this formula, and I can now say that because the thickness is given and the diameter is a function of the length, I can say that I as a function of x is equal to pi times t divided by 3. And then diameter is the function of x that we developed before. And I'm going to put that in that parenthesis, dA plus x over L, dB minus dA, parenthesis, and then cubed. Now I can plug this into my integration formula and integrate that with any values that I want. So anyway, this is a very handy equation that you should probably have some knowledge of. Anyway, hope that will satisfy our video lecture, and please email me if you have any questions, either before or after the exam on Tuesday.